a blurb about Flow. Flow is a seminar focused on federated learning. We try to build, attempting to build a global community surrounding research topics that touch on federated learning, and we're not focusing on a single one. So any of those many topics that do touch are welcome, including learning algorithms, privacy, personalization, cryptography, systems, hardware, anything you can think of. It's great pleasure to have Adam Smith, who's a professor of computer science and engineering at Boston University, speaking today. So Adam is very well known in the area of data privacy and cryptography, one of the leaders in this domain, and he works on these topics intersected with many areas such as data science, quantum computing, statistics, machine learning, and so on and so forth. And today he'll say something about his recent work. I understand this is recent work on memorization of examples in machine learning. So Adam, again, it's a great pleasure. Go ahead, and I'm looking forward to the talk.
Well, thank you very much. Thanks for the introduction and for the invitation to come and speak. This is a nice opportunity. I will be speaking about recent work with Gavin Brown, Mark Bunn, Vitaly Feldman, and Kunal Talwar. The work is on the memorization of training examples by learning algorithms, and I'll explain exactly, what I mean by that as the talk proceeds. So let me see my control. There we go. So machine learning models always contain some information about their training data, sometimes a lot of information. And the basic gist of this work is that we provide natural settings where the memorization of essentially entire training examples is provably necessary, no matter how the learning algorithm works. And even when a lot of the details, the memorized details, are ultimately irrelevant to the task at hand. So I'll explain what all these words, what I mean by all these words as I go through. But this is the general thrust of the talk. All right, now, it's well known that machine learning models will often memorize training examples, sometimes very explicitly. If you think of like a nearest neighbor classifier, it's not hard to see how the description of the classifier is more or less an exact description of the data set. It's not just in these sort of low dimensional settings that this happens. You also see it, for example, with support vector machines, where the typical way you present the solution of a support vector machine is in fact in terms of the so-called support vectors, which are explicit training examples from the data set. But memorization often happens in more subtle and implicit ways. So for example, Carlini, Liu, Erlingson, Kos, and Song last year, or year before last, gave an example of how language learning models would typically could be sort of made to memorize random strings in their input data, even when it's clear to someone like on the outside, to any human, that this stuff that it's memorizing is irrelevant to language understanding. Okay, these are just like random strings of digits. And this was this type of memorization was memorably depicted in this nice XKCD cartoon where a bunch of revolutionaries are caught using Smart Compose. So this is sort of more the kind of memorization we'll be talking about, and sort of what I mean by irrelevant to the task at hand, I will formalize soon. Now, there's another phenomenon that's received a lot of attention in the literature recently, and that's the issue of how machine learning models will often perfectly fit their training examples. So, classic theory tells us that perfect fitting is actually overfitting, and it's not generally the best way to get a model that generalizes well. But there's been a lot of recent work, notably this work of Zhang et al., but also a bunch of follow-ups trying to understand why it is that with current deep learning architectures, it's often the case that to get perfect accuracy, to get the best possible generalization error, that is, one pushes the model into a regime where there's sort of near essentially perfect accuracy on the training examples. Okay. So what this phenomenon corresponds to has been called memorization, but it's just memorization of training labels. And actually, my collaborator Vitaly Feldman at a paper last year showed that there are natural problems where this type of memorization of training labels is actually necessary, no matter how the algorithm works. What we do in this work is to generalize this to understand when it's actually necessary for the model to memorize entire examples. Okay, so I'm going to walk you through several versions of the result, starting with something that is kind of not actually all that interesting through to the main result, which I feel is interesting. But the basic setup is going to be the same in all of them. We've got a data set X consisting of n rows, n training examples. And each row consists of some vector of, we'll call it D bits for simplicity, together with some labels that will either be generally be binary, but sometimes will be more complicated. And a good parameter setting to have in mind is where the dimension is much larger than the number of examples. It's not the only one in which our results apply, but it's maybe the more interesting. Okay, so this data set is fed to a learning algorithm that comes up with a classifier or a model. And then the measure of success of the model is when you run it on a fresh test point that ideally was drawn from the same distribution as the original data. Then it should correctly predict the label. Okay, so there is a, oops, sorry, over here, there's a distribution P on the left. I think you can see my cursor when I move it around. And so we'll assume that the training examples are drawn from some population, which we'll think of as a probability distribution P, and we'll assume that the test data, for the purposes of measuring accuracy, the test data are drawn from the same distribution. All right. So the error of this model is just the probability that it correctly predicts the label. Okay, just the normal measure of generalization error. All right, so the question we're interested in is, what does this classifier, the description of the model itself, tell us about the data set X? And our main result, essentially, is that there are natural problems such that every learning algorithm that is sufficiently accurate, let's say it's within error 0.1 of optimal, will encode lots of information about its training examples. So like one formalization of that is to look at the mutual information between the data and the classifier. And this is the sort of Shannon's measure of mutual information, a classic measure of correlation between random variables that in actually several senses measures the number of bits of information about X that are contained in the random variable M. Okay. So one simple version of the result is that there are natural problems such that for every learning algorithm that's sufficiently accurate, the model encodes lots of information about the training data. Okay, there are n times d bits of information in the training data, and it encodes some constant fraction of that. Okay, so this result on its own is actually, as stated here, is actually not that interesting, I claim, and that's because it's not clear what the model. Maybe the model is not memorizing stuff about the training examples, but in fact learning things about the underlying distribution. It could be that all the information about X that happens to be in M is actually about the problem at hand, and so it's exactly what we want the model to learn. So we actually prove a stronger statement that I'll try to walk you through. So there's a natural problem Q And what I mean by a problem here is it's like a meta distribution on distribution. So what Q is is like a distribution on problems that the learner could have to solve. Okay, I'll explain that a little more in a second. So for every learning algorithm with error that is, close to optimal, the mutual information between the training data and the model, even given a description of the labeled example distribution, P, has to be large. So, okay, so let me just sort of talk through the symbols in this. So, so we'll think of there are two distributions that we're dealing with. One, an instance of a learning problem is a distribution on labeled examples. So that's the distribution, that's the population from which these and the training examples are drawn, and the test example also. And what we want is that even given the full description of the labeled examples, of the distribution on labeled examples, the model has to encode a bunch of other information about X. So like the mutual information between X and M is high, even when I condition on the training distribution. And in order to formalize that, I have to say, where does this training distribution come from? So we'll assume that it's chosen from this meta distribution Q. Q can depend on N and D, and so that's why there are subscripts there for Q. And then we're going to compare the performance of the model to the best possible average error of any model on this meta distribution. So the learning algorithm is being compared to the best it could do, sort of on average over like instances drawn from this meta distribution Q. And what we're getting is that under this setup, there's lots of information in the model about the data, even after you condition on the instance distribution on labeled examples.
Can I ask a question?
Is there a question? Yeah, absolutely.
Yes,
Interruptions are welcome.
So I have one question. So can you say something more or not in the case when the error is known to be 0, let's say?
When you mean the optimal error is known to be 0?
Yes, the opt-n.
So in our case, we can make the optimal error arbitrarily close to 0. But if it's exactly 0, our particular examples won't really work. That is, and if it's known to be, but that doesn't mean, I don't know, is the short answer. It may well be that one can get non-trivial results of this form, even in what learning theorists would call the realizable case, where the labeled example distribution is actually perfectly labeled by one. So
what you're saying, it might be a more complicated case, not a simpler case. So you say that your construction doesn't extend to this case. I thought that maybe something stronger could be even said in that case.
Yeah. So that's correct. In some sense, what happens in most of those settings where the labels are perfectly realizable by a function from the class, what tends to happen is that the learning algorithm, at least in the types of examples we played with, the learning algorithm will kind of pick out the right labeling function, and in particular, eventually it will learn enough to ignore the data. So it'll basically learn something that is effectively a description of this of capital P, and doesn't have any information beyond that. And so once you condition on P, the mutual information between X and M would be close to 0.
I see.
I suspect one could come up with other examples.
Okay.
Maybe I'll say more about that later in the talk.
All right, thank you.
Yeah. Okay, so So when I say that the model stores information that's irrelevant to the task, this is what I mean, that the mutual information between X and M is high, even condition on P. So this is sort of the first version of our result that I consider interesting. And we have a second, stronger version, which is in a bit more detail what actually goes on. So there are natural problems Q sub NDs, the same setup as before, for which every data set has a special subset, which we'll call the singletons. And I'll explain what that means in a few slides. So these are the special training examples. And the setup is such that there are lots of these training examples. And furthermore, that not only that there are lots of the training examples, but they're very rich in information. So even conditioned on the problem, they have a lot of information in them. And any algorithm that does sufficiently well, on average, has the property that it encodes essentially all the information about those training examples. So not just a constant fraction of the information, but like almost 1 minus little o1 fraction of the information about those examples is encoded in the model. So those specific examples are basically perfectly replicated in the model. And something we have, I don't have experimental results in this talk because the sort of slides weren't ready, but we've been running some experimental some experiments to see how this plays out with sort of practical deep neural architectures. And and in fact, for the problems we consider, all the architectures we tried, like not only memorize the training examples, but it's very easy to extract a full description of the training example from black box access to the model. Okay, but we'll talk about that a bit. So this is the basic result, that there's a large subset of the training examples about which the model basically captures full information, retains full information, even though the details of those examples are not ultimately relevant to the task at hand. That is, if we had more data, if we had like infinite amount of data, we would eventually just learn a description of P, and we wouldn't have to have any information about any other information about X in the model. But what our results show is that with finite samples, you need to encode a bunch of information that's really specific to your training examples in order to perform well. So this is really the main result.
Just a very
yeah,
quick
more
question
questions are welcome.
Just very quick one. So this so does this mean that the age given h of s given MP would tend to go to 0, right?
Yes, that's correct. H of s given M and P would be, and in particular, actually H of s given M would, just M even, would be nearly 0.
Okay.
That's correct. Yeah. Okay, and also, like, for the examples we come up with, another kind of funny thing about them is that if you had full information about the distribution, you could come up with a very short model that labels the data essentially perfectly. So in our case, so yeah, in some of these cases, the like the error, the realized error, the error of the optimal model, not given like a finite number of n of samples, but given like many samples, ultimately the error would be 0 if you had infinite amounts of data. And furthermore, the resulting model you would have would be very short. It would have almost no dependence on the dimension d. It would be just basically independent, only depending on n, like n log n bits or something. Okay, so what I want to do is kind of give you a flavor of what these problems look like and why this phenomenon occurs. And then I'll talk a little bit about what light I think it sheds on the kind of problems we face in machine learning and the kinds of problems that we face when we come to privacy, making machine learning algorithms, training machine learning algorithms on sensitive data. So And you know, Peter, thanks for the questions so far, and all of you who keep them coming, I'm happy to take questions as the talk proceeds. Okay, so the learning problems we consider have this flavor, have a kind of all that we consider several, but they all have the same flavor. In each problem, the data is a mixture of many different clusters of different weights. Well, they can be of the same weight too, that doesn't really matter. Mixture of many different clusters. And so different clusters will have like different numbers of training points from that cluster. And the sort of meta problems we look at are specified by first giving some kind of distribution on the mixture coefficients, on the coefficients of this mixture model. So like the relative weights of the different parts of the distribution. It turns out all of our statements work with just a uniform mixture on n components in the distribution. So, you know, if it's easier just to think about that, you don't have to worry about it, although there's some interesting implications when you get these kind of long tail distributions on the mixture coefficients. And then within each component of the distribution, there's a separate, there's a like the distribution on labeled examples for that component. And each of those is going to be selected from some family randomly, from some meta distribution. And it'll be like a different labeled example distribution for each of the components of the mixture. And we look at two very different types of like subproblems within each component. Okay, so again, within each kind of cluster of the distribution, we've got a different just like learning problem, a different distribution on labeled examples. And here are the two main ones we consider. The first one is what I'll call hypercube clusters. Okay, so within each component of the distribution, you get the following structure. So an example is a binary string, and it comes with a label that tells you what component it's from. Okay, so the label tells you the component, which I'll call J. And then within that component, there's a certain number of positions that are fixed to specific bits, and everything else is chosen randomly. And so we call these hypercube clusters because if you look at like for each index J, you've got a uniform distribution over some hypercube in 0, 1 to the D, meaning there's a certain number of positions that are fixed and the remaining positions are uniformly random. Okay, so in this type of problem, it's effectively, you can think of it as kind of a clustering problem. The example tells you that, sorry, the label tells you what cluster the example came from. And when you're given an unlabeled example, your job is to figure out which cluster it came from. Okay, the other type of problem which we consider is kind of inspired by string completion and the kind of things that like Smart Compose looks at. So, so in these problems, we'll call them next bit prediction problems. Within each cluster, there's some secret, not secret, but like not visible, hidden string C sub j. So it's a string that's specific to that cluster. And the examples one gets are generated as follows. Within each, if an example from this cluster is generated as follows, first we choose a random length L between 0 and D minus 1. And we get an example by flipping a bunch of bits from this underlying string C. So each bit gets flipped with some probability delta, a little less than a half maybe. So that generates an example, which is like a noisy version of some prefix of C. And then the example comes with the string J. So the learner knows which which component of the distribution that a training or a test example comes from. And the label is the next, or a noisy version of the next bit of C. Okay, so the label is the this next position of C. So like the learner's job given an unlabeled example is to predict the next bit in the sequence. Okay, and what it sees in its training data are noisy prefixes of that sequence. So once it's seen many of them, then it basically will learn C exactly. But when it's given only a few examples, it's got a more challenging problem to deal with. Okay. So for both of these problems, what we basically show is that in those components of the distribution where there are relatively few training examples, the learning algorithm has to memorize those training examples perfectly, or nearly perfectly. So these are the two flavors of problems. So one, a kind of a more like a supervised clustering type problem. The other one, a string extension problem, next bit prediction problem, or think of it as like, you know, completing a sentence or something like that.
And just for clarification, if I may,
yeah.
so memorization, you always mean this is this conditional mutual information.
That's right. So
right,
so
the one that you introduced at the beginning.
That's right. So I mean, it's also true without the conditioning, but it's less interesting without the conditioning, because without the conditioning, you might just be learning about P, which is what you want to do. Right. Yeah. So every time I say memorization, it's that sort of conditional notion of memorization.
Yeah, and when you say memorize, you essentially say there's some kind of lower bound, which is good in some sense, right? On that.
Yeah. So specifically, if I just go back, you know, what we show are statements of the form of this form here, so that there's this like set of examples about which the condition, the model, even conditioned on P, the model encodes like all of the information about S, or actually in this version, you could remove the conditioning. The model encodes all the information about S, even though a bunch of that information is sort of not relevant to P. Yeah. So that's the kind of statement we
right, and you don't care about the properties of F other than this one.
Yeah, F is just, I just don't want to write down like a big complicated formula. So yeah, it's just like something that's going to zero. It's generally something like, yeah, it's something like square root of epsilon or cube root of epsilon in the particular problems we consider.
All right.
Yeah, and the exact form of that function F depends on the problem, and in some cases it's only conjectured to have that form, and I'll say more when I get there. Okay, so the idea is that the sort of the learning problems we consider, you've got these mixtures of different components. A typical data set has many. The way we set it up, like for example, if there's a mixture of n components, and I'm drawing n training examples from the distribution, then for many of these components, I'll just have a single training example from that component. And so we'll call these singletons. So these are the singletons are the training examples that are the sole representatives of their cluster or their component in the training data. And these singletons are the values that we argue that the model has to retain most of the information about. So here's our learning algorithm up in the top right. And what we prove is that the learner has to, memorize these singletons to perform well on test points for that cluster, for the cluster from which the singleton comes. And in order to perform well overall, the learner has to perform well on average over the clusters from which it got training data. And so that means for most of the cluster, because there are many clusters that only have one training example, in order to do well overall, the learning algorithm has to do well on most of those clusters, most of those singletons clusters. And so that means that it has to memorize lots of information about these singletons. So this is the intuition for what's going on in all of our arguments. And I would claim, so I'll try to formalize a bit more about this in a few slides, but I would claim that at this level, I think the framework is very intuitive. Like it's sort of not surprising to think that this long tail problem where you've got in your training data many points that are like the only representatives of their type, then you have to remember a lot about those those training examples, right? So if I've got an image classification problem, if I only have one picture of a cat, you know, I'd better hang on to that picture just in case, because I don't know what it is about this picture that makes it a cat, right? And so I better just hang on to the entire picture. And if you think of the way, you know, those of you who've raised or spent time with small children, you know, you see this with little kids when they're learning language, when they'll hear like some new phrase. And they don't even know if it's like one word or multiple words, but they'll just like retain the phrase as a chunk. And they'll repeat it until you correct them and tell them it's actually several different words, right? Like they'll just like latch on to things they've heard. And if they've only heard one example, or if they've only heard that phrase like once or twice, they'll just remember it like as a sound bite and try to reproduce it. Right? So it's a very natural structure of problem, and I think it's very natural that there's sort of no better strategy than to like keep those singleton examples around in their entirety. Okay, so I'd like to spend a few minutes discussing the related work, of which there's quite a bit, and and discussing the result a bit, and then I'll talk about a bit more about like the technical part and the kind of the lower bounds, communication complexity lower bounds. And again, questions are welcome, and I'll kind of keep going, but I'm happy to stop and discuss or answer questions as we go. Okay, so related work. So I mentioned this work of Feldman from last year that looks at memorizing training labels. And this paper that I'm talking about was very much inspired by that one. And in particular, the sort of mixture structure we use comes from that paper, but then what's going on inside each component is more complicated here. On a more technical level, it turns out there's a line of work on learning algorithms that leak relatively little information about their data. And this is sort of in the same sense that I gave here, like conditioned on the problem distribution. And some sort of a similar work by, so the learners that leak little information, that was originally by Raif Basili and co-authors. Raif was a former postdoc of mine. And then there was follow-up work by Nachum Schaefer and Yodayev, and by Livni and Moran, which is not exactly on information theory, but has implications for our setting. But basically, what those papers show, they look at a couple of different settings, but very similar to ours, but they give bounds of the form omega of n log d. So that's the lower bound. And the strongest thing that one can get from their results, even if you kind of work at it, is a lower bound of the form n log d. So like much less than n times d. Okay, so just the way their framework is set up, you don't get the kind of complete memorization that we're talking about, although certainly their results hint that there's something interesting going on there, and their techniques are interesting. And I guess we didn't really know about their paper at the time we started working on the project, but like in retrospect, there's a lot in common between the papers. Another thing that's really another nice line of work that is relevant here is work on what's called the representation complexity of a class of functions. So this was started by Baymel, Nassim, and Stemmer in 2013 and extended by Feldman and Xiao in 2014. And these papers give lower bounds on the size, the size in bits of the model that is required for learning a particular concept class. Okay, and those results have information theoretic interpretations in terms of bits of shared information, but they're about that. What they really lower bound is the mutual information between the model. Sorry, this is a typo on the slide. This should be the mutual information between M and P. Sorry, not X and P. So they lower bound the mutual information about the labeled example, the example distribution that has to be contained in the data in the training. Let me try that again. The mutual information between the distribution on labeled examples, so the description of the distribution, and the classifier. But they don't actually show that there's information memorized by the classifier that's not specific to P. In fact, in all of the examples they give, the sort of information that's retained by the classifier is only about P. Okay, so in some sense, it's easy to throw away the extraneous stuff in their examples. Nevertheless, some of the proof ideas we use are similar and inspired by those papers. Another relevant sort of line of work that's kind of quite different, it seems at first glance, is on time-space trade-offs for learning. So that started with this nice paper of Steinhardt, Valiant, and Weger, and there was this breakthrough result by Ron Raz giving a lower bound for learning parity in a streaming model. So those, what those results show is that when as you're passing through the data set in doing your learning, you might require the memory of your streaming algorithm might be required to be much larger than the size of the final model that you arrive at. And our results are really doing something qualitatively different, meaning that what we're interested in is like, how big is the final model and how much information has it retained about the data that it just passed over? Even if and it can pass over, you know, however many times it likes. And so at first glance, it looks like these things are kind of, we're looking at different quantities, but I think there's a fair amount of affinity between the kind of proof techniques and kind of thinking that goes on. And in particular, I suspect that our results have some interpretation in this streaming model, but we haven't worked that out. Okay, there's a lot of other information on a lot of other related work on connections between information theory and learning that I'm not going to go through in detail, but certainly these were all topics that came up in our discussions, and you know, we were definitely sort of inspired to frame the question the way we did by a lot of this other work. So what are the main implications of our results? So, you know, maybe one very straightforward implication is that giant models may well be unavoidable. Namely, you know, for example, you know, one language model that's been discussed a lot, even in the popular press recently, is GPT-3, which is it's a general purpose sort of language model that can handle a bunch of different tasks. But the biggest version of GPT-3, uncompressed, takes 700 gigabytes. So it's got a huge amount of information. And what our results show is not only do these, for natural problems, these models have to be big, but it's entirely plausible that they, in order to achieve the kind of performance they do, they actually have to encode lots of really specific details about their training examples. And actually, around the same time as we published our paper, Carlini and others came out with an experimental paper looking at GPT-2 and GPT-3 and showing that indeed they could extract from the description of the model things like specific people's addresses and phone numbers and various like pieces of text people had written in emails that were that they stuff that they saw was in the training data and they just found sitting there in the model. Okay, so there's some experimental evidence that this happens with these big models. And what our results are about is, the question we're asking is it unavoidable? And the answer is, well, in some cases, yes. All right.
So again, a quick question.
Peter.
So
yeah, sure.
Do you believe, I'm sorry, I'm asking
no, questions
so
are great.
So is there any indication that the learning problem behind GPT-3, I mean, there's many uses, of course, but let's say pick one, has the kind of structure, probabilistic structure, of course, not one of these two examples that you give, but somehow the kind of structure that you would expect that this would happen?
Well, yeah, I mean, I guess we chose our problems to kind of represent tasks, to be representative of the kind of tasks that people try to tackle these days with machine learning, with supervised learning. So, for example, one of the problems is sort of a stylized abstraction of sentence completion, where you're trying to predict, whatever Smart Compose does if you use Gmail, where it tries to. Is it
what you were trying to do, or this is kind of a I mean, it is constructive proof, but you were trying to construct an example of a task so that you could say there exists. I mean, in some sense, one want to be happy even with existence of such a thing. So did you try to purposefully build something that looks like an actual task?
Yeah, we were definitely looking for tasks that smelled like the things we actually want to do with data, as opposed to like, I don't know, algebraic problems or learning parity or stuff like that, which are, those are interesting existential results, but then they don't feel quite as informative about like the kind of things we do on a daily basis. So we tried to choose things that were stylized enough and abstract enough that we could actually prove things, but problems where we felt it shed light. Of course, that's subjective, and you can decide that you don't think it shed light on the problem, but that's of course in the eye of the beholder. I think Aurélien had a question. I saw a hand go up and then disappear, so I don't know.
Me too.
If he had a question. If
not, I think I clicked on him. Aurélien, you can unmute yourself, or I can unmute you. So where is he?
He says he can't.
Okay.
Okay. Hey, can you hear me?
Yeah. Hi.
Okay, great. Hi, Adam. I guess this is more of a comment related to what you were discussing. So there is also some other, I think, quite interesting recent experimental work that goes, I think, in the same direction. Like paper showing that basically by extending like a neural language model with a nearest neighbor model, basically, so some things that will interpolate between the two, then they show they can improve a lot, for instance, in predicting essentially rare patterns. So essentially this kind of long tail stuff that you refer to.
Interesting, yeah.
Cases. And so in a way, this is also some kind of evidence that memorizing at least part of the training set can help, and that maybe even some of these big language models maybe they do not even memorize enough in a way.
Yeah, interesting. Yeah, I'd love to see the paper if you can send me a link or something.
Sure. Yeah, I think it was.
But yeah, that sounds very much in line with the kinds of things we've observed, and that I think there's sort of a if you talk to people who work in machine vision or natural language processing, this sort of long tail problem is definitely like a big focus right now of trying to understand how to modify the models so that they perform well, not just on the kind of the well-populated parts of the distribution, but also in these kind of sparser regimes where the regions where there's not as much data, and how to like transfer, for example, representations that you've learned using in the kind of better populated parts of the distribution to these sparser regions. And I think what happens as a result of that is that you end up with these, you know, encoding a lot more information about these training examples, which is, you know, and I understand why they do it, although I think it's certainly problematic for privacy. Yeah. So, yeah, just speaking of privacy, you know, I think what our results suggest is that there are sort of aspects to the difficulties of private data analysis that at least we, the authors of the paper, hadn't really appreciated previously. So on one hand, you know, one can interpret the lower bounds we give as impossibility results for differentially private learning, and that's because any differentially private algorithm necessarily has relatively the output of the algorithm encodes relatively little information about the training data when the training data is drawn from some distribution. But I think perhaps you know, I'd say as lower bounds for differential privacy, these results aren't that interesting. What I think they do is sort of highlight an aspect to like the privacy, the difficulty of doing things privately that wasn't as appreciated before, at least by us. And it's sort of, in particular, like with the learning problems we give, it's sort of not obvious a priori that, especially for the clustering problem I told you about, it's not obvious a priori that the output has to be like really high dimensional. It's not obvious. In fact, if you have enough data, you can come up with a relatively compact model. And so it's sort of like it's a different type of problem from the problems for which we've typically proven lower bounds before. Those problems were usually about like showing that when the thing you're outputting is a very rich summary of the data, you know, there are many different statistics you're trying to summarize, then you can't do that accurately. And this is a sort of a different flavor of lower bound and a different flavor of issue. And I think what it says is that there's this natural inclination when you're analyzing a data set to sort of cut it up as finely as you possibly can, subject to getting statistically reasonable results in the various pieces of the data. Okay, so if you look at the way, for example, sociologists analyze, you know, data about voting patterns in a country, you know, they'll chop them up as finely as they possibly can down to the level of, you know, neighborhoods in a city, and they'll just go as they'll keep on like slicing the data up into smaller pieces until the pieces get so small that they're right at the limit of what they can do anything reasonable with from a statistical point of view. And I think in the machine learning community would, you know, tend to do the same thing. And what our results show is that that's like inherently a problematic approach if you're concerned about privacy, that like you're sort of pushing yourself into these settings where it's really hard to not contain, you know, not reveal lots of information about your data points. All right.
So can I have a question, please?
Yes, yes. Questions are welcome.
Yeah, so can you please comment a bit about maybe like about connection to federated learning? So maybe you described before that you might have those clusters, like they have like very few data, and this might kind of represent the clients. Also, there might be some clients within like federated learning that have very, very few data. So essentially, like what you were saying is that, okay, you cannot really have a good performance, like good global model without really having a lot of information about those like clients and their private data, right?
That's correct. Yeah. So a good way of thinking about this in the setting of private learning is of federated learning is that if you want one global model then it's at least for the problems we're talking about, then there's some subset of clients for which that global model has to basically reproduce all the data. I think what our result in the federated setting, I think what our results point to is the value of personalized models, where what you use the global information for is to, find good representations and stuff like that can be used at the, in initial models that can be used at the client level that can be refined at the level of the client. I don't know if we've really mined all the connections to all the implications for federated learning. I think it's a good question.
Thank you. Thank you.
Okay, so just a brief word. I'm basically out of time, so I'll just speak briefly about at a technical level what's going on. So what the main idea is that we give lower bounds for this memorization. We show memorization is necessary by giving lower bounds on the information complexity of a kind of some specific two-player games that are related to the classification tasks we're dealing with. So one of those games is sort of a one-shot version of the next bit prediction problem, the next symbol prediction problem I talked about. And then one of them is is like a nearest neighbors problem. So I think I'll skip the next symbol prediction because I think it's less interesting. And I'll talk about the the nearest neighbors problem and a conjecture we have, an open problem. Okay, so recall the hypercube clusters problem. So in this case, you've got a bunch of components. Within each component, the data are uniform, subject to a certain number of positions being fixed. Okay, so within each component, there's a set of fixed positions, and that set is different from component to component. So what we do is the way we get a lower bound is by saying, well, suppose Alice were to get only singletons. So suppose Alice, I've got two players now, Alice and Bob, and now Alice is going to get some amount of training data, but each of her training points will be alone in its cluster. And what Bob gets is he gets one unlabeled example from one, but it comes from one of the K clusters that Alice got data from. Okay. And it turns out that if you can solve the main problem well to near optimal accuracy, then you can solve this singletons only version of the problem also to near optimal accuracy. So like you can't solve the big problem without being able to solve this singletons problem. So I'm not going to explain why that is, but that's relatively straightforward. What we observe is that actually in this singletons problem, it's actually a nearest neighbors problem. So if you consider this setting, then it turns out from Alice's point of view, her data is just drawn completely uniformly at random. That is, the fact that there are some components that are shared within a cluster, some positions that are shared within the cluster doesn't help her because she only gets one component from each cluster. So only one training example from each cluster. And if you look at how Bob's example is distributed, it's actually, so like here are Alice's data values floating around in space. The way Bob's example is distributed, it's as if someone had taken exactly one of Alice's examples and obtained Bob's data point by just flipping each bit with some probability close to a half. Okay, so again, once you're in the singleton setting, it's actually there's sort of not really what's going on are not really shared positions, are not really fixed positions, but it's rather more like a binary symmetric noise model. And so Bob's task is actually a nearest neighbors task. So if Alice and Bob are solving this problem well together, then Alice is giving Bob enough information to figure out which of her data points is closest to his. it turns out like that's the problem they have to solve. And that's the problem for which we give lower bounds. So here there's a gap between what we can prove and what we think is true. So what we can actually prove for this problem is weaker than what I'd really like. So what we can show is that if Bob succeeds with near optimal probability, then the mutual information between the model and Alice's data, whatever Alice sends to Bob and her data, is k times d, so that's what we'd want, times some constant that is, the best thing we can prove is actually less than 1. So it's like a little less than a half. Sorry, a little more than a half. But what we actually conjecture is that it's in fact 1 minus little o of 1. So the way we prove the thing we can prove is using what's called the strong data processing inequality. So it's this sort of information theoretic inequality that happens to work really well in this setting. But it's sort of fundamentally limited to achieving this constant of 1/2 log 2. But what we conjecture and what our experiments support, I don't have slides on the experiments, I'm sorry, is that in fact the required mutual information is very close to k times d. And furthermore, we actually think that there's that one can say something about efficient recovery, that given a message from Alice to Bob that allows Bob to solve the problem well, one can actually reasonably efficiently recover strings close to the xi's from Alice's message. But that's something we're, again, working on, and we're not sure exactly what the form of that statement would look like. So I will, I started a couple of minutes late and I'm finishing late. I'm sorry, it's 9 o'clock or Eastern time anyway. But I'll just wrap up with a couple of conclusions. So memorization is sometimes necessary. As I said, privacy is even harder than we thought. I think the proofs and the approach give us some insight into what features of a problem lead to memorization and why we tend to see these giant models that really do memorize in practice. And there's some reason for optimism. So one thing that is true in our problems is that if you're willing to settle for suboptimal accuracy, even a little bit suboptimal, by like, let's say, instead of you're within 0.1 of optimal, you're within 0.2 or 0.3, then you can actually you can solve the problem well in the well-populated regions of the data with very, very concise models that memorize very little. And I think we're seeing that a little bit with some of these highly compressed models that are going on phones right now, for example. There's a lot of work going, when resources are constrained, people come up with super compressed models that don't do well on everything, but do well in the areas where there's enough data. And I think that our results support optimism that will progress and that we'll see more of that type of more success along those lines. So I will stop there. Thank you very much, and I'm happy to take a few more questions if people have time.
Thanks a lot. This was very exciting and inspiring to the community, I think, at least to me. Samuel, if you could unmute everyone and allow people to ask questions as they wish, I think this would be best.
Yeah, so if now anybody can unmute themselves.
All right, so while people are unmuting themselves, a quick question. You say that you're running experiments at the moment. Can you verbally describe the kind of
Yeah, I can tell you. I mean, they're more or less complete. I just didn't have them in a form that I could present. Yeah, we're looking at, so in the experiments we're looking at, we're generating data according to these synthetic distributions that I described. And we're just seeing, like, if you take state-of-the-art architectures and just train them on this data set, these types of data sets, what happens? And, well, first of all, they don't do that well because they're not but you have to, there's some tuning that goes into getting them to work on these problems. And what you tend to see is actually memorization starts happening long before the models get any good at the task. So what tends to happen is, first you get to a point where it's easy to extract from the model the training data. And then, after more epochs of training, you get an iteration, you get to a point where.
How do you extract the data in practice? What do you do?
Oh, so we look at a few different extraction strategies. So one is just like for this, if I go back for this problem, this isn't exactly the thing we run experiments for. This is like the subproblem for which we can prove lower bounds, right? We run experiments for the whole problem, but like this picture is useful. So what we do is like for the clusters that have only one or a couple of data points, we look at what are the we seek to find a value of y, like a test point that maximizes the likelihood that a particular label will be predicted. So you look for the test point that maximizes the probability of the label, and it turns out that test point is generally like exactly one of the training data points.
Interesting.
We do some other things that are like that, where we take many random points, and for many random points, we look at the direction that will improve the likelihood of a particular label as much as possible, like roughly a gradient, and then average all those things to tell us like what direction are they all pointing on, and if you sort of average the directions they're pointing in, they're all pointing at like exactly the training label, the training example.
Yeah. And
so
when
we
you
have
say
like a couple
memorization
of
occurs
strategies.
long before, and when you say memorization happens long before these models are getting any good, what do you mean? So
we're looking at sort of
80%
like
accuracy, or what kind of a thing?
Yeah, I wish I had
6C.
Okay, so I don't have the numbers in front of me. I think it's like this is a multi-class problem, so you can have like very low accuracy. So their accuracy is sort of like sub 5%, and they're already memorizing. And then, but after enough training, they classify it to accuracy, 70, 80, 90%, depending on how we set things up.
All right.
So it's sort of, yeah, we're I don't know. I don't have the plots and to show you. So
no, this is good enough. This is good enough. So I was just.
One interesting question is sort of like what is a nice natural data version of this experiment? Like if you're going to play with real data sets, where would you find these types of phenomena? And there, I think actually this recent work on analyzing GPT-2 and GPT-3 is probably like a pretty good example of how to do that. It's a really nice paper.
Hey, maybe
Hi, Aurélien. Hey.
One question now. Thanks again for the very nice talk. So maybe I want you to come back a bit, maybe to these implications for differential privacy, because I'm not so sure I got your point there. So you were saying essentially that these can give lower bounds for differentially private learning, like lower bound on the error, which seems kind of natural, I guess, to some extent. But you were saying something related to the high dimensional output. So the fact that maybe it suggests that maybe the lower bounds that we know for some lower dimensional problem are not tight, or I don't know, maybe you can.
No, so I guess what I meant to say here is that like a priori for example, with the hypercube clustering problems, there does exist a small model that labels the data pretty well. And so a priori, it's not obvious that you would, that like in some sense, what's going on in a lot of the lower bounds for differential privacy is that you're producing some very high dimensional output. And so in order to, there's sort of a general wisdom that if the like thing you're really after is sufficiently low dimensional, then you shouldn't need a lot of data to learn that. And in some sense, what we're showing is that, yeah, the thing you're really after is low dimensional. That's great, but like given n data points, you can't find that low dimensional representation, right? So even forget privacy, right? Like that's what our lower bounds show, is that given a finite sample size, you actually need a very big model with n times d bits of information in it. Even though the real model, if you want to perform near optimal accuracy, even though like if you had more data, you would eventually come up with a much more compact model.
I see.
And so, yeah, so that's sort of a different thing than what, like normally for the most of the problems I've seen lower bounds for say differential privacy, it's sort of clear what the like right size of the thing you're after is. And that's often the source of the problem, right? Like if you want to produce many separate estimates of like separate statistics. Yeah.
I see. So it doesn't really, in a way, doesn't really challenge the bounds or their tightness or anything like that.
No, I don't.
The way we typically think about these limited cases.
I would say, yeah, that the interest here is not like, I would say as a lower bound on differential privacy, these results aren't necessarily, like we kind of already had lots of natural problems for which we knew differential privacy was difficult. I think this is just the structure of these problems is different from the kinds of problems people had considered previously. And I think reflects like a thing people try to do in practice, which is fundamentally like problematic for privacy, which is to really try to like subdivide the data set as much as possible and get these sort of like very fine-grained picture of what's going on.
Right. I guess one could argue also that having to memorize, especially these kind of long tail example, might be especially bad for privacy in a way, right? In many
yeah, I mean the people most
problems.
Needing protection, right. In many cases, those singleton examples correspond to people from, say, vulnerable subpopulations, or people who kind of are outliers in one way or another in the population, and possibly those are the ones where we'd be most concerned about privacy. And what this says is that those are the places where it's possibly hardest to protect.
All right, thanks.